of a conductor depends. Let us perform a simple activity to understand about the factors on which resistance of a conductor depends. Let us take a thin copper wire of length L. Connect one of its end to the negative terminal of a battery. Connect its another free end to the positive terminal of battery through a switch and an ammeter. Now allow the current to pass through the wire by closing the switch. Note the current displayed by ammeter. Now open the switch and replace the copper wire by another copper wire having same thickness but length twice the previous wire, that is 2L. Again, note down the ammeter reading. Now replace the wire by another copper wire having larger cross-sectional area but length same as that in the first case, that is L. Take note of the ammeter reading. Now replace copper wire by a nichrome wire of same length and area of cross-section as in first case, and note down current flowing in circuit through ammeter. What do you observe? Is current flowing in the circuit same in all the cases? No. You will observe that when length of the wire is doubled, current flowing through it becomes almost half. Also, when area of cross-section of wire is increased, keeping its length same, current passing through it also increases. Even variation in current is observed on changing material of wire by keeping its length and area of cross-section same. From the activity, we can clearly say that current is inversely proportional to length of the wire, that is, I is proportional to 1 upon L. Also, current is directly proportional to the area of cross-section of the wire, that is, I is proportional to A. But according to Ohm's law, current is inversely proportional to resistance, that is, I is proportional to 1 upon R. Comparing above equations, we get R is proportional to L. Let us name it as equation 1, and R is proportional to 1 upon A. Let us name it as equation 2. Hence, we can say that resistance of a conductor depends on length of a conductor, area of cross-section of a conductor, nature or material of conductor. Combining equations 1 and 2, we get R is proportional to L upon A, that is to the area of cross-section of the wire, that is, I is proportional to A. But according to Ohm's law, current is inversely proportional to resistance, that is, I is proportional to 1 upon R. Comparing above equations, we get R is proportional to L. Let us name it as equation 1, and R is proportional to 1 upon A. Let us name it as equation 2. Hence, we can say that resistance of a conductor depends on length of a conductor, area of cross-section of a conductor, nature or material of conductor. Combining equations 1 and 2, we get R is proportional to L upon A, that is, R is equal to rho into L upon A. Here, rho is the constant of proportionality and is called resistivity of the material of the conductor. In the equation, R is equal to rho into L. R is proportional to L upon A, that is, R is equal to rho into L upon A. Here, rho is the constant of proportionality and is called resistivity of the material of the conductor. In the equation, R is equal to rho into L upon A, that is, rho is equal to R into A upon L. SI unit of L is meter, that is M. SI unit of area is meter square, that is M square. While that of resistance is ohm. Hence, SI unit of resistivity is ohm meter. Resistivity is the characteristic property of the material. Metals and alloys have resistivity in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter, which is very low. Hence, metals and alloys are good conductors of electricity. On the other hand, resistivity of insulators is of the order of 10 to the power of 12 ohm meter to 10 to the power of 17 ohm meter, which is very high. Hence, insulators are poor conductor of electricity. Resistance R and resistivity rho both depend on the temperature of the material. Let us see electrical resistivity of some substances at 20 degrees Celsius. We can observe that resistivity of an alloy is higher than that of its constituent metals. Hence, alloys do not oxidize easily at higher temperatures and so are commonly used in electrical heating devices such as electric iron, electric heater, electric oven, etc. Let us now solve a numerical problem based on the topic we discussed.
If the length of a wire is 50 centimeter and radius is 0.5 millimeter, find the resistivity of the wire if its resistance is 30 ohm. Solution. Let us first write the given data in proper units. Length L is equal to 50 centimeters, equal to 50 into 10 raised to minus 2 meters. Radius r equal to 0.5 millimeter, equal to 0.5 into 10 raised to minus 3 meters, equal to 5 into 10 raised to minus 4 meters. Resistance R is equal to 30 ohm. We want to find the resistivity of the wire. The resistivity ρ is related to the resistance R, length L, and area of the cross-section by equation. R is equal to ρ multiplied by L upon A, 1. Ρ is equal to R multiplied by A upon L, 2. Let us first find the area of the cross-section of the wire. As wire is cylindrical in shape, its area of cross-section is given as A is equal to pi r square. Therefore, A is equal to 3.142 multiplied by 5 multiplied by 10 to minus 4 on the whole square is equal to 3.142 multiplied by 25 multiplied by 10 raised to minus 8, which is equal to 78.55 multiplied by 10 raised to minus 8 meter square. Let us substitute the values of R, A, and L in equation 2. Ρ is equal to 30 multiplied by 78.55 multiplied by 10 raised to minus 8 divided by 50 multiplied by 10 raised to minus 2. Ρ is equal to 47.13 multiplied by 10 raised to minus 6 ohm meter. Hence, the resistivity of the material of the wire ρ is equal to 4.71 multiplied by 10 raised to minus 5 ohm meter.